Okay, well, thank you, Eric. As was mentioned, my name is Eric Stellwagen. I am the Vice President and a co-founder of Business Forecast Systems. We're the company that produces the Forecast Pro software. I've been working in the field of forecasting for quite some time. Prior to my position here, I was working in an engineering company developing forecasting software for the electric power industry. And in 1986, we started Business Forecast Systems with the idea of creating business-oriented forecasting software to make statistical methods accessible to a general business audience. And that's what Forecast Pro is all about. So today we are going to talk about components of data. And this is a roadmap of how we're going to be spending the next hour or so. We'll start pretty general, and we'll look at the different components that are present in most data sets. So as Eric mentioned, these are things like trends, seasonal patterns, response to promotions, and other components which we'll go through as a list. There is a little bit of construction going on in our building today, so if perchance you do hear some background noise, that's what it is. Hopefully the workmen will keep it to a minimum. But here's how we're going to spend our time. We'll start off by really surveying the different components that are present in data, and we'll look at a lot of examples. And we'll talk about both the form of the components as well as their stability. And so you'll get a feel for this as we go through. We'll also be introducing a new model, a new forecasting method, which we call the custom component model. And it's actually under development currently. It will be in the next version of Forecast Pro, but we'll include a demo of that technique, which exploits the different components. After the presentation, we will take some time for questions and answers. And as Eric mentioned, you can ask questions via the chat box at any point that they occur to you. And we'll, at the end, again, go through some Q&A. So let's begin by looking at some of the different components. What components are there? Well, trends. We'll have a definition for a trend in a minute, but most people conceptually know what a trend is. It's going to be upward or downward movement to the data. Seasonal patterns. Are there times of year that you sell more than other times of year? So this is a repetitive pattern based on the time of year. Cyclical variation, and really what I mean by this is the business cycle. So are we driven by the economy? In times of recession, do our sales go down? In times of expansion, do our sales go up? Many of us may have products that are driven by the economy, and some of us will have some that really aren't. But again, we'll consider, is our demand being driven by the economy? And if so, how do we approach forecasting it? Trading day variation. This may be new to some of us, but the question is, are there things about the calendar and the way the data are collected which should be taken into consideration as we generate a forecast? We'll see there are different types of trading day variations. For instance, sometimes manufacturers might have a production calendar where it's more convenient to work in entire weeks, and so we end up with what is often called a 4-4-5 calendar, where either 4 full production weeks or 5 full production weeks are in each period. So it's kind of monthly in the sense that there are 12 periods in a year, but it's not based on the Roman calendar. That's an example of trading day variation. Another one might be, say, a retail store that might be closed on Sundays, for instance. So all of a sudden, the number of days that we're open becomes a factor when we want to generate a forecast. So again, we'll have definitions for all of these components and examples of all of them. Another one that we're going to look at is events. So these are things that hit the data, that have an impact, and then generally go away. Sometimes these are referred to as interventions as well. Product promotions would be a good example of this, or a business interruption, something that occurs, it has a definite impact on demand, and then it dissipates. The last component that we'll be considering is noise. And noise is usually the part you can't explain. It's the random variation that exists in the data. And what we'll see is that noise, although we can't explain it and we can't forecast it, we can measure it. And by measuring the noise in our data, we get a feel for expected forecast accuracy. So noise is important, and we will spend some time with it. And these are the components which we are going to cover. So let's start with trend. So here's a definition for trend: the tendency to increase or decrease over the long run. So what we're talking about is upwards or downwards movement that is sustained and that needs to be forecasted. So the forecast will have either an upward or a downward trend to it. If we're forecasting a trend, it can take different forms. One form is linear, meaning a straight line. So I can forecast a straight line trend. You know, you might do that with a ruler. You know, what's our best fit line? Another type of trend would be an exponential trend. If something is growing as a percentage of itself, then it grows much more quickly than a straight line trend, and that type of growth is referred to as an exponential trend. Another type of trend I might want to forecast is a damp trend. A damp trend is a trend that starts off linear, but then dies out over time. Some people call this a bent trend as well. So we have these different forms of the trend, and when we're forecasting trends, we have to think about what types of trends exist in our data and how do we want to project them going forward. So the form is important. Now let's look at some pictures here. The first one is it's quarterly data. It's sales tax revenue from a state. And you can see that the trend here is we're using just kind of our best fit line. So it's just a straight line trend. And you can see that it fits the data reasonably well. So it does appear two things. One is that a linear trend is probably appropriate here. And second, that it's global. It's pretty much the same trend from start to finish. More on this in a minute or two. But our forecast is for a linear trend going forward. And again, a linear or straight line trend is one example of form. The second example here is earnings per share for IBM. And I think it's on an annual basis. And what you can see is that the growth is much more fast, or much faster than linear. And we have this kind of exponential growth. So this is an example of an exponential trend. And rather than getting a straight line trend, we have something more aggressive than that. You want to be very careful when forecasting exponential trends. You want to make real sure that indeed something is growing exponentially before you actually commit to that kind of a forecast. The final example is sales of a product, and it's a good example of a trend that changes a lot. So if we look at the history, you can see the trend is at times pretty aggressive. It sort of levels out. You know, there's a moderate trend in this section. It's kind of pretty level here, but it's a changing trend. Overall, there is sustained upward movement here, but again, I'd say it's much more local. We forecasted it using a damped approach. So the initial trend starts off reasonably aggressive, but it dies out pretty quickly. So again, what we're looking at is different types of trends, and specifically at the form of the trend. And these are the common ways to extrapolate trends from historic demand: as a straight line or as a linear trend, as something that's growing as a percentage of itself, an exponential trend, or in a damped fashion, one that starts off linear and dies out with time. The other thing we want to look at when we're looking at trends is, are they local or are they global? And so the concept here is something is global, it's from start to finish. It's an unchanging trend. If something is local, then it's changing in time, and we want to emphasize more recent history more strongly than, say, the past history. So here's another example. This data is from Nike, so it's I believe it's total revenue, and you can see it's in the 80s and early 90s. And you can see in the beginning of the data there is a bit of a trend here for the first few years, and then it's maybe just slightly trended but reasonably flat here in 83, 84, 85, 86, 87. And right around 88, it just explodes, and the trend changes. And we have a very aggressive trend throughout the late 80s and early 90s. This is the period where Michael Jordan became their spokesperson. And they paid him an awful lot of money to do it. And it looks like he was worth every penny because it really changed that company. And it's a good example of a trend that's changing in time. Now, if we're going to forecast this, what's important is that we think about, are the trends local or global? The blue line shows what happens if we do, say, a best fit line in Excel. So we just regress it against a trend line. And it's clearly not appropriate for this data. Okay? The resultant forecast starts at the wrong point, and it really undershoots a great deal. And if we look historically, there are times where we're undershooting, there are times where we're overshooting, but in general, the problem is that the trend is changing in time, and our forecast model for that component, for the trend component, is not. The red line used something called Holt exponential smoothing, which allows the trend to change in time, and you can see it fits the data much better. So that as the trends are changing, so is our forecast of them, and so is our fit. And the forecast that we have at the end is a local estimate of the current trend. So again, we talk about the form of the trend, whether it's a linear trend or an exponential trend or a damp trend. We also think about, is it local? Do I want to be emphasizing the most recent history in coming up with what the trend is currently? Or is the trend pretty stable and unchanging, and I can use a great deal of data? In this case, clearly the trends are changing, and we want to emphasize current conditions and recent history. The next component that we'll consider is seasonal patterns, seasonality. So this is a regular intra-year pattern. It's repeating itself. And again, are there certain times where we sell more than others? Now, why are data seasonal? Well, there's lots of reasons why they might be seasonal. So here's a list of some of them. One of the things that can impact sales, let's say that you're selling snow shovels or down parkas or maybe cocoa or hot beverages. The weather. When the weather gets colder, some of these sales are going to become more prominent. Flu season. If I'm working for, say, a pharmaceutical company and we have drugs that are, say, flu shots or vaccines, then clearly the flu season is going to be a factor. The first two examples here, the weather and the flu season, are examples of what I call non-calendar-based seasonal patterns. In other words, there are times a year where it gets colder or hotter, and that may drive our sales. And there are times a year where maybe it's the flu season or maybe it's, hay fever or whatever it happens to be. And they occur roughly the same time every year, but not necessarily always the same month or the same week. The other ones on our list, things like holidays, the school calendar, tax season, the end of the model year, if we're doing, say, automobile sales, these are things that are more calendar-based. If I'm working for, let's say, a toy company, so we manufacture toys, and we're based in North America, what is going to be my best month? Well, it's going to be December. I'm going to sell more toys in December than any other month. Why? Because in North America, Christmas is always in December, and it's our big holiday as far as toy sales are concerned. And if I'm working for a toy company, I have what I would call calendar-based seasonality based on that holiday. On the other hand, again, if I'm working for a pharmaceutical firm that's doing flu vaccines, then what's my best month? And the answer is sometime during the winter. So maybe it's December, maybe it's January, maybe it's February. It might vary from year to year. It's always in the winter, but it's not tied to the calendar. It should be pretty easy to comprehend that if something is absolutely tied to the calendar, it's going to be easier to forecast. It's easier to forecast the timing of toy sales, which are going to peak in December, than, say, vaccines, which are going to peak in the winter but not necessarily in December. Okay, so one of the things when you think about seasonal patterns that we think about is, are they tied to the calendar? Or are they tied to things that are seasonal but not strictly to the calendar? The other thing we think about at times is that a lot of forecasting methods will use what's called an index approach to capturing and to forecasting seasonal patterns. And this is not true of all forecasting methods, but it's true of many. And usually there's two different index approaches. So in an index approach, you're going to have some sort of an adjustment. Let's just think about monthly data. So each month is going to get an adjustment, either up or down, for the seasonal pattern. And if we're using an index, it's usually either what's called a multiplicative index or an additive index. And we can use a picture to show this. But with a multiplicative approach, what we would do is to have an index for each month. So let's say we work for that toy company and we sell 20% more toys in December than every other month. If we have an index for December, which would be 1.2. If you multiply something by 1.2, it increases it by 20%. Perhaps February is our worst month. It's a short month, for example. It might have an index of, say, 0.9. If we multiply by 0.9, it's going to pull it down by 10%. But the important thing is that each month will receive some sort of adjustment for the seasonal component. In this example, it's actually a pretty famous series. It's called the airline series, and it's international flights out of Heathrow Airport in the it looks like 50s and early 60s. And you can see it's a very regular series, but it also is a clear example of a multiplicative pattern. This peak to trough variation, notice it gets bigger and bigger. So up here in 1960, that peak to trough looks like to be about 250 units, whereas back in the 50s, it was more like 50 units. And if we have a multiplicative approach, if we're multiplying these factors in, we get this kind of fanning out. As the series grows, we're taking 20% of a bigger and bigger number, so that as the series moves upwards, the seasonal variation grows as well. And the quick way to think about this is the seasonality is a percent. Okay, so it's a percentage-based approach. The alternative is less common with business data, and it's an additive approach. And this is an example here. And notice the peak to trough, even though the data is growing, is constant. So it's always about the same whether we're at the beginning of the data set or the end of the data set. So here, instead of multiplying in by indices, we might just add. So we'd sort of add, 300 units for December, subtract 100 units for February, that kind of thing. But again, what we're looking at is this peak to trough variation, and whereas in the top example, it's becoming more pronounced as time goes on, that's indicative of a multiplicative pattern, versus the bottom example where it's pretty uniform, which is, again, an additive pattern. So wrapping up on seasonality here, again, we think about the different causes. Are they tied to the calendar, or do they vary? We think about how we're going to approach it. Should we think of seasonality as a percentage, or is it sort of a factor that we add on or subtract off? The next component we'll consider is the economy. Okay, so I have this labeled cyclical effects. But what we're thinking about now are changes that are associated with the economy. The economy goes through cycles. There are periods of expansion and there are periods of recession. If we're in a period of expansion, then we refer to this as a cyclical upturn. But the idea is that we're going to be growing faster than we normally would because the economy is doing well. The opposite of that is a cyclical downturn, where the growth slows down because we're going into recessionary times. So typically, as you look, if you graph macroeconomic variables, indicators of the economy, what you'll see is it's a cycle. And the question is, are your data impacted by this? So let's look at a data example that is. This data is actually, it's sales of insulation that goes into industrial buildings. And the data come from the 80s, where we had a period of recession. And you can see that in periods of recession, there aren't as many commercial buildings being built, and the demand for industrial building materials was falling. The recession basically went through here. You can see the data starts to recover about here, so in sort of mid-83 or so. And we were coming out of the recession. We actually came out of that recession a little earlier than that. It was probably in late 82 that recession really started ending. The sales of the materials did not immediately rebound because, again, this is insulation. So if we start constructing buildings, the first thing we do is not buy insulation. That comes in about 12 months later as the building's nearing completion. So the recovery in this actually lagged behind the recovery in the economy. And for forecasting purposes, this is important. First of all, if we have a business that's being very much driven by the economy, we need to pay attention to the economy. And we also want to know what kind of relationship do we have. Do changes in the economy impact us right away? Are they concurrent? Or is it a sort of a lagging relationship where the economy changes and then we feel the impact of that later? And oftentimes, if you're forecasting things that are driven by the economy, you want to do it with like regression techniques, for example, where we might be able to bring in indications of the economy. And here's a list of what's called the leading economic indicators. Basically, the concept here is if we look at what these things represent: plant and equipment contracts, new building permits, changes in inventory, changes in pricing, changes in borrowing. It's pretty easy to think that if we see changes in the number of plant and equipment contracts, say it's increasing, that we would expect that that's going to spur economic activity going forward. If we see more building permits being issued, then we'd expect that improvements in the economy will follow. So these are what's called the leading economic indicators. And people watch these types of variables as a way of trying to determine where the economy is going. How do they use them? Well, there's a couple of different ways to use them. One is to use what's called the Leading Economic Indicators Index, or the LEI. And basically, it's a weighted average of these. And so economists will often look at the LEI as a way of trying to track changes, upcoming changes in the economy. There's also something called the diffusion index, which basically says how many of these are improving and how many are not. So we're just looking at the percentage of the indicators that are rising. And again, we look at this as a way of predicting where the economy is going. How well does it work? Okay. People vary on their interpretation of this. My outlook on this is based on studies that were published in the International Journal of Forecasting at periodic intervals. And my own feeling is it doesn't work very well. So what the economists really want is to be able to watch the LEI, that leading economic indicator, and if you see 2 or 3 consecutive months of declines, then you say to yourself, we're going into a recession. And so there was a study that said if we go back in time and we look, how often did that formula work? In other words, kind of after a cookbook here. And the recipe says 2 or 3 consecutive months of decline indicate a recession is coming. And the good news is if you actually look at this historically, you can indeed forecast the timing of every U.S. recession since 1948 when the study was done. The bad news is you would have also been forecasting recessions when they didn't occur. So the declines occurred, but the recession didn't. So that's what we call a false positive. We expected to go into a recession, but we didn't. And that leads to this clever phrase at the bottom that economists have forecast 14 out of the last 10 recessions. Okay, so it's kind of a good news, bad news scenario. And furthermore, to get these results, which I would call not great results, they had to loosen up some of their assumptions. So that last bullet is saying the lead time by which the LEI predicts the turning point is highly variable, unlike its reputation for the economy, for leading the economy by 6 to 9 months. To me, 6 to 9 months is already pretty vague, and loosening that up to get again 14 out of the last 10 recessions is not a great track record. The other thing I would point to is that very often when you ask authorities, you go to leading economic forecasters and you say, where are we? They often don't agree about where we are. Are we in a recession? Are we bottomed out? Are we starting to recover? You ask different people, you get different opinions. If it was as easy as just watching the LEI and knowing where we are, you wouldn't get such a diversity of opinions about not just where we are going, but actually where are we now. And for those of you who were following politics with the first George Bush election, so this is George Bush Sr., the economy, that was a big theme of that election, is sort of it's the economy. And everybody was coming out saying different things about the economy. People were saying, we're in a recession, we're not in a recession, we're coming out of a recession. There was, again, no agreement on this. So bottom line here is forecasting the economy is difficult. And if your data are being driven by the economy, then you've got a pretty tough forecasting job on your hands. If they're not, and there are lots of things that are not being, demand is not being driven by the economy, then we can ignore it. If you are, then you either have to keep your forecast pretty short term, because your current trends will reflect current conditions pretty well, or you need to be providing scenarios for how the economy will change. So our next component here is trading days. And again, I know this will be new to some, but not to all. But basically a data set, or a time series, can exhibit what's called trading day variation. And this occurs when the demand periods might vary in length, or when subdivisions of the demand periods are not uniform. What do I mean by that? Well, let's think about that. And let's think about some examples, okay? I've already mentioned previously one of them, which is a 4-4-5 production period. So again, if my forecast periods either have 4 complete weeks or 5 complete weeks, then it shouldn't be hard to understand that periods that contain 5 weeks of demand are very likely to be much higher than periods that have only 4 weeks of demand. Okay, so this is not really due to the seasonal pattern and the seasonality that we talked to before. It's due to how we collect our data, and that sometimes we use 4 weeks and sometimes we use 5 weeks. But certainly we can't ignore it because it's going to make a big difference. What about the number of working days, or the number of days in a month? Let's say my data is not seasonal. On the other hand, when I look at sales in February, I'm only open for business, say, 28 days, whereas in December I'm open for 31. So all other things being equal, I would expect to sell more in December than in February, due to the fact that there's more days in December than there is in February. So the number of days per month, or maybe the number of working days per month, might be another example of trading day variation. So usually in that kind of scenario, we're talking about a few percentage points difference based on the length of the month. But again, a few percentage points improvement is often something you want to do, and so it's certainly worth looking into. Another thing that sometimes occurs is the question of not all days, for instance, are created equal. If I am running a business, let's say that I'm running a car dealership, and my best sales days are Fridays, Saturdays, and Sundays. That's where I sell the most cars, okay? Then the mix of days per month becomes important. So let's think about December. December has 31 days in it. If December were to start on a Friday, then December would have 5 Fridays, 5 Saturdays, 5 Sundays, and 4 of every other day. In, say, the next year, it starts on a Monday, then I'd have 5 Mondays, 5 Tuesdays, 5 Wednesdays, and 4 of every other day. So my first scenario, where December started on a Friday, is a stronger December for me in terms of trading days because Fridays, Saturdays, and Sundays are my big selling days, and I've got 4 of them in that year versus the year where December started on a Monday. So it's another example of trading days. It's not really the number of days that's important. It's the mix of them. And again, there are lots of industries where you might have higher demand on, say, the weekends or on a weekday, depending on the nature of your business. So this is something to consider. Usually, if we've got trading day variation, how do we approach it? Often you can use something called a weighting transformation. And what we want to do is to convert or remove, let's say, the trading days. So for example, if we had monthly data, so we have an observation of demand month by month, and we were to, say, divide that observation by the number of days per month, we would convert our monthly demand into a monthly observation of demand per day. Essentially, we get rid of the fact that the number of days vary from month to month. We forecast that, and then as a final step, we multiply back in the number of days, and that converts it back into demand by month. This is called a weighting transformation, and it's an example of what's called a reversible transformation because I can transform the data, forecast it, and then reverse it. It's built into Forecast Pro, and it's an easy thing that you could do in Excel as well. But again, the concept is we divide through by weights to remove the trading day impact. We forecast the series, and then we reintroduce the weights to convert it back to the original metric. Our next component, events. Events are things that occur, things that happen, that have an impact on our data and that can't be ignored. They may or may not be repeated. What are some examples? Probably the most common example that we come across in our business is product promotions. So if we run a price promotion, it increases demand. Or maybe if a competitor runs a promotion, it might decrease our demand. But product promotions are an example of an event, something that occurs that changes the demand and that we can't ignore for forecasting purposes. Holidays that move. So Easter or Rosh Hashanah, for example. If I'm in, say, a business that's in the food and beverage industry, then holidays are real important. People buy a lot of food and beverages during the holiday seasons, and I need to watch, timing of something like Easter because my forecast is going to change depending on what month it falls. If I'm working with weekly data, then things move around a lot. So, for example, here in the United States, our big summer holiday is the 4th of July. If my products are being impacted by the 4th of July and I'm forecasting on a monthly basis, I don't have to worry about it. It's always in July, and it becomes part of the seasonal pattern. But if I'm working on a weekly basis, then I might need to pay attention to where the 4th of July falls because it's not always week 27. Sometimes it might be week 28. Sometimes it might be week 26. So if I'm working on a weekly basis, I need to pay particularly close attention to things like holidays that can move around. Other examples of events. Say a natural catastrophe. We have an earthquake. We have a tropical storm. Maybe that takes down production and puts a hole in our demand figures. Maybe it's the opposite. Maybe we're in I'm running a roofing company, and after a tropical storm, there's more demand for my services, so it actually increases demand. But there are lots of things that fall into the category of what I would call events. They are things that happen. They hit the data. They have an impact, and then when they're over, that impact disappears. It's important to capture them in your forecasts. And let's look at an example. So here's a data set. The data comes from Tupperware, actually, which is a company that sells containers, and they do it through parties. And if we look at this from a component point of view, you can see there's really not much trend to the data. It's pretty flat. It is seasonal. We can find patterns here that repeat themselves every year. So it's definitely a seasonal thing. But the first thing that your eye probably noticed was this great big spike. And if you look carefully, you can see it's actually 2 months. This month here and the month before are both substantially bigger than all the other months. And this is an example of an event. And in this case, the event was a giveaway. If you go to a Tupperware party, you get a free gift. And if you went to a Tupperware party in January of 2013 in this particular country, this SKU, this product, was the free gift. And so they've included with the demand, included with their sales, are what we would call free goods, things they gave away. And there are lots of industries that have free goods. Pharma is a good example. We've got doctor samples as well as, say, prescription fills. And usually you keep them separate and you forecast them separately. Tupperware really can't do that. If we subtract out what was given away, we'd be far below regular demand because some of the people that would have bought it received it for free. So it's kind of a harder problem for them, and they have to treat it as an event, and it's important to capture it. Now, if you ignored that, and so I built a model here in a forecast where I just ignored that event. And you can see I get a very poor forecast. I've got this great big spike next January, which is kind of an echo, if you will, of this spike. If it's going to be the free gift again, that's too small. It should be way up here. If it's not going to be the free gift, it's way too big. It should probably be down here. But again, it's an example of an important event and what happens if you ignore it. If we forecast it, or we model it, here's an example of we build what's called an event model, which has knowledge that these events occurred, and we get a forecast where we assume the event is not occurring in the future, which is much more typical demand for this item. I should mention that a lot of the solutions that I'm talking about, event modeling, regression modeling, weighting transformations, these are all methods that we've actually covered in webinars in the past and that are available on our webinar archive. So if you wanted to learn more about modeling events, for instance, there is a recorded webinar on event modeling which you may want to visit forecastpro.com and watch for more details. So here our emphasis is really on introducing the components, not so much on the details of how we model them, but recognizing the components and being able to work with them. The last component that we're going to cover is what's called noise. Okay, and here's a dictionary definition of noise. It says irregular fluctuation accompanying a transmitted signal but not relevant to it. Okay, we have today, I think we've got about we had about 380 people sign up for the webinar, and a certain fraction of our audience out there is going to be engineers. For the engineers out there, it's signal to noise ratio. They already know what noise is. It's a common concept. For the non-engineers, it's random variation. So we have certain things in the data that we're interested in understanding. Okay, we call that signal. So what are the things we want to understand? Well, our components: trend, seasonal patterns, trading day variation, events. These are all the different signal or the different things that we want to understand and forecast. But there's also stuff we can't explain, just random variation. This is the noise. And so it's the things we can't capture. It's a nuisance. It makes it harder for us to understand. If the data are noisy, if there's a lot of random variation, it makes it harder to understand the actual structure that's there. Okay? So what do we do about noise? We can't really forecast it because it's random variation, but we can measure it. And by measuring the amount of noise in the data, we can determine things like the uncertainty around the forecast. So let's look at an example of this. Here's an example. This is an annual data set. It is centimeters of rainfall in Brazil, in sort of a certain region in Brazil where it rains a lot. And as we look at the data, it's averaging about 150 centimeters per year. But any given year, it might jump around quite a bit. So here's 250 centimeters. Here's only 50. So there's a lot of variation here, and it's not predictable. It's random. This is an example of a very noisy data set. What's our forecast? Our forecast for next year is 150 centimeters plus or minus 100. Okay, you see these confidence limits, the blue lines, how wide they are? And what it's saying is the data are very noisy. It's very hard to forecast this with any sort of accuracy. If this were, say, one of our products, and it was this noisy, what it's telling us is we need to carry a lot of safety stock if we're going to meet demand here. There's a lot of period-to-period swings, and so there's a lot of noise. It tells us the forecasts are going to have a lot of uncertainty around them. Here's a data set we looked at before. This is the international flights out of Heathrow Airport. It's the opposite. It's all signal. All of this is structure. There's trend, there's seasonal pattern. We just look at the data, and it's a highly predictable pattern. Our forecast is for that pattern to continue, and look how tight those confidence limits or blue lines are. We can forecast this very accurately. Why? Because there's not a lot of noise, and therefore we can really understand the components of the data. So again, the first example where we have a lot of noise, a lot of uncertainty, very large confidence limits and safety stocks. Second example, very low noise, much easier to forecast accurately, and therefore the confidence limits are much, much tighter. Okay, so that's our survey of the different components. Different forecasting methods take different approaches to generating forecasts. Some methods, and notably exponential smoothing, take a component-based approach. In a smoothing approach, which is smoothing is the most widely used of the statistical forecasting methods, and again, it is a component-based approach. It's a form of extrapolation. So it uses the demand history, and if we're doing events, it also looks at an event schedule. But basically, what we do is we estimate each component, and what we're after is what's called final values. What is the component at the end of the data set? And the components it works with are level, trend, and seasonal, and potentially events if those are present as well. So use the data, which in turn we calculate the final values, and we use the final values to generate a forecast. This often works well in the short term, where the current conditions, the current trend, the current seasonal pattern, etc., can be reasonably expected to continue. Now we're going to look at an example. And so let me call up Forecast Pro here. This is a telecom series, so it's from a telecommunications company, and it is installations. It's people going out into homes and installing services. It's on a monthly basis, and I want you to think about components here. First of all, most of us would look at that and say, well, clearly it's trended. And if we look a little closer, you can see it's pretty flat in the beginning, and then this trend sort of emerges. And I would definitely say if we're going to forecast it, we want to forecast a trend. So one of the components we want to capture is trend, and it's a local trend. The trends are changing in time. So we want to emphasize current history more than past. Another is the seasonal pattern. If I start looking at some of these peaks and troughs, these troughs are all Decembers. Okay. We don't install as many phones in December as we do in other periods. That makes sense, again, with all the holidays. And that puts it's one of our causes for the seasonality. All the other ones we looked at, many of those would come into play as well. It's probably calendar-based. Okay, most of our seasonality would be calendar-based. Trading days. Yeah, this is installation data. So trading days are probably a factor. We can't really see that visually here, but it is there, and I have worked with the data, and trading days does account for some variation. Okay, let's forecast this. And so I forecasted this using exponential smoothing, again, a component-based approach, and it's continuing that trend, and it's continuing the seasonal pattern, and we get a very reasonable-looking forecast. What about our confidence limits? What about our noise? They're pretty wide. they're not as wide as that rainfall in Brazil, but there's a fair amount of plus or minus because, again, the data they exhibit a fair amount of noise. So, again, I could probably improve this a little bit by adjusting for trading days, but this is just an example. And what I want to point out is the components are pretty predictable, but there's also a fair amount of noise. If I look at the model itself, and again, we have a webinar on exponential smoothing for those who want to get into more detail. You can go to the website and it's recorded. But here are the components that we've been modeling: level, trend, seasonal. And they're exhibited with their final values. So the final value of the level is 65,000. So that's right about here. That's the starting point for our forecast. The final value for the trend is 780 units per month. So we're going to increase by 780 units per month. And the final values for the seasonal indices, there's one for each month: January, February, March, April, May, etc. These are multiplicative. So notice, for instance, March index is 1.08. If you multiply something by 1.08, you increase it by 8%. So it's saying that March, we're going to sell 8% more due to the seasonal component than we would on a typical month. Notice December, 0.81. If I multiply something by 0.81, I'm going to lower it by 19%. And what we're saying is we're going to sell 19% less in December's due to the seasonal component. So again, we generate this forecast. It looks pretty reasonable. It extrapolates the current local trend and the current seasonal pattern, and we're doing a 12-month forecast, and everything looks pretty good. Now, what if our boss says, well, I don't want a 12-month forecast. I want you to forecast out the next 5 years. So I'm going to change that forecast horizon to 60, and I'm going to rebuild the model. Okay, and here it is. So now I've forecasted out the next 5 years using a component-based approach. Now I think I have an issue. Do I really think that linear trend is just going to continue for the next 5 years? That's pretty aggressive. And again, what I want to point out is, in the short term, it's probably pretty reasonable to think that the current conditions on the components will continue. In the longer term, it becomes more tentative. So I may want to change the longer term forecast in some way. And I'm going to go back to our slides and introduce something that we have under development currently called a custom component model. And it's one way of customizing certain components. So this will be introduced in the next release of Forecast Pro. It's currently available in beta test form. If you're a Forecast Pro track user and you want to get an advanced look at this, we can arrange that. The model allows you for some of the components to be estimated from the data and for other ones to be customized by the forecaster. Okay, we'll see an example of this in a minute. The model can be useful in a lot of different situations, and again, we have beta testers starting to use it now, and they're using it for a lot of different things. One is the example we have on the screen just a minute ago, which is customizing the trend for a longer-term forecast. So I'll show you that one in a second. But again, often for longer-term forecasts, the simple extrapolation of the current trend is not going to be realistic. Another is, what if the data are very short? And for instance, I know the data are seasonal, but they're really too short to capture the seasonal pattern well. By customizing the seasonality, maybe I could use the seasonality for, say, a group level data or for a different product that have more history that I think will be similar. Here's another one that comes up a lot. I've never promoted the product, but we're going to next year. And so how do I forecast that event component when it's never occurred? Okay. So these are just some examples. There are many others of instances where you might want to change some of the components in the forecast period. And let's show you how this new model works. So I'm going to go back to Forecast Pro, and I'm going to go into what's called the custom component model. And again, this is in beta test at the moment. And what I want to notice here is we have, let me go ahead and commit to that, we have a current forecast, and that green line here is the underlying trend, and the red line is the forecast. And it has different components. First of all, it has a starting point, which is about 65,000. So that's right here. Okay. And that could be customized. So I could put in a different starting point, or I could use the final historic value if I want. But if I do automatic, it's saying calculate it from the data, which is what it's doing. Then there's the trend. Currently I've got a linear trend that was automatically generated, but I could have a different kind of trend. The form could be different. I could have a customized linear trend, or I could bend it. I could have it go up or down. We'll see this in a minute. Seasonal patterns. Here's the seasonal indices. It was done automatically, but again, I might want to customize it. And finally, events. If I have an event schedule with different promotional events, I may want to adjust those too. So we'll do a couple of things here. Let's start by exploring changing the trend. I'll go to a custom linear trend, so it's still going to be a straight line trend, but we can play with different parts of it. We could change the ending point. So we could pull down, for instance, this final value of the trend to something lower. We could change the slope of the trend, which is currently 742 units a month. We could look at the total forecast, which is 5.3 million, and say change that and adjust the trend accordingly. I'm going to change the slope. So instead of 742 units per month, so let's do 300. And what you can see is that trend changed. Okay? And so now we've still got the 5-year forecast. We're still using an automatic starting point. We're still using an automatic seasonal pattern. If we had events, we could use automatic events. But we've changed the slope. We've customized it. Alternatively, let's go back to the automatic for a second. What if I wanted not to have a linear trend but a bent one? I could change this in different ways too. Let's do the total forecast. Currently that forecast is 5.3 million, and let's change it. Let's make it 4.5 million. So I'll commit to that. And what that'll do is to bend that trend so that the total forecast sums up to 4.5 million. It's just an example, but it's an example where we looked at our 5-year forecast, that linear trend, and maybe our market research and our management and such says that's not sustainable. We need to bend it. We need to change it. And this gives me a way of maintaining certain components being derived from the data and combining it with others that I might want to customize. And then finally, let's do one more thing with this. I'm going to call up this particular example. What if we had some events that occurred? And in this case, we've got some product promotions. They've never occurred historically, but we know we're going to do a special. We're going to do a price promotion, and it's actually, I would show you the schedule, but for the sake of time, I'll keep going here. This month is going to be promoted, and I've indicated that. And there's a competitor promotion, actually I think it's on this month, and because it's never occurred historically, we can't estimate it from the data. So what I'm going to do instead is to go in and put a custom entry in there. And maybe looking at similar promotions in other territories, let's say that the increase there was 5%. So I'll put in a value of 1.05. And maybe when the competitor promotion would run for a similar region, it pulled our sales down by 10%, so I'll put in a 0.9. But the point here is we can't estimate those impacts from the history because they've never occurred. So we're going to put them in. And we're kind of merging, if you will, quantitative information that's being estimated from the data with some qualitative information that we're entering. If I commit, let's watch this data point in particular. When I commit to it, you can see it changes. It went up by 5%. This one, which had been up here, went down by about 10%. But the important thing, again, is we're customizing our approach to a component-based model. All right, let's go back to our slides. And we're coming to the end of our presentation, and we're getting ready for questions. So if you do have questions, be sure to submit them if you haven't already. And let's sort of summarize what we've been talking about. When we look at data, and when you look at your data, it can contain different components. And it's really important that we think about that. and we understand the components that are present. The form of each component can vary. Trends can be linear, trends can be local, trends can be global, trends can be bent, okay? Trends can be exponential. Seasonal patterns can be additive or multiplicative. But the form of each component and the stability of each component can vary, and it's important to understand that. Component-based models such as exponential smoothing are going to use the historic demand to estimate current conditions and to forecast them going forward. And they often work quite well in cases where there's a lot of continuity between the past and the future. And they're very commonly used in important forecasting methods. On the other hand, there may be times where estimating all of the components from the demand history is not really possible. Maybe I know there will be events in the future, but they haven't occurred in the past. So I really can't build a statistical model for what's going to happen. At times, you could combine qualitative and quantitative component forecasts. So I'm using, from the historic demand, I'm getting the trend and the seasonal pattern, but I'm bringing in to bear on that some of my own knowledge and say, market research on the event side. And this is a powerful combination. Okay. So again, I want to thank everyone for coming to or attending today's webinar. I'm going to present a couple of slides that are talk about our next webinar and some of the events that we're holding, and then we'll open it up for questions. So the first thing I wanted to mention is this webinar series is a quarterly series. We have one every quarter, and the next one will be in April 16th specifically. And it's going to be on confidence limits, safety stocks, and order quantities. So it's looking at the plus or minus around the forecast. You know, how the forecast is more than just a number. And how do we use these types of pieces of information to make better decisions. The webinar will be presented by James Berry, who is the Director of Training here at Business Forecast Systems. He's very knowledgeable on this subject, and it promises to be a good and informative webinar, so we hope you'll sign up. And if you'd like to, I realize it's 3 months away, but if you sign up today, we'll send you reminders. And you could go to forecastpro.com and sign up, and we'll keep you posted. The other thing I wanted to point out, for those of you who are not familiar with Forecast Pro, it is the package that we were using in the examples at the end there. If you are interested in learning more about the software, we'd love to help you out there. And probably the best way to learn about it is with a live demo. And we do them over WebEx. And if you're interested in getting a live demo of Forecast Pro, actually you can even just type it into the chat box, and we'll have probably one of our sales guys follow up with you and schedule it for you. There's also a lot of information on forecastpro.com, including some video tours and just printed information. So if you are interested in learning more about the product, by all means, we encourage you to learn more. We'd love to tell you about it. Also, Business Forecast Systems, my company, offers training and workshops in the area of business forecasting. This can be on-site or remote. But if you are interested in training, either product training or workshops on forecasting, let us know. We'll be happy to help. We also have other resources. You'll find a lot of educational material both on our website. We also have a blog called The Forecast Pro, which has encourage you to visit that and check that out. We have a YouTube channel with a lot of recorded video presentations. And in general, forecastpro.com is the place to start if you're interested in learning more. So in addition to software, we do a lot of education, and I would encourage you to take advantage of some of the free materials that we have up on the site. Finally, I want to mention we have scheduled the Forecast Pro User Conference for 2015. It will occur in Boston on September 29th and 30th, so it'll be a 2-day conference. It will be a lively event, and we'll have presentations from Forecast Pro users and case studies on how they've implemented the software and how they've implemented their forecasting processes. We'll have some tutorials on things like forecasting methods and applications. We'll have panel discussions. We'll talk about product direction. We'll have social events. It'll be a lot of fun. And if you are interested, we will keep you informed. As someone who signed up for the webinar, you'll get some announcements via email. And if you are interested in participating, like if you'd like to present a case study, let us know. We'd love to hear from you. We'll also be running a pre-conference workshop the day before the conference, so a full-day workshop that'll be covering the different forecasting methods that are found in Forecast Pro, so exponential smoothing, Box-Jenkins, event models, the component model, lots of other models, and the emphasis will be on conceptually how do these models work, and more importantly, perhaps, how do we apply them effectively for our own data. So if you're interested, it promises to be a fun event, and we'd love to see you there. So mark your calendars. Okay, we've gotten to the end here of the formal presentation, and it's time to field some questions. And Eric, what do we have for questions?
Okay, well, we've run a little bit over, so I say we'll do 2 questions here.
Okay.
And so we'll start with this one. How can you determine when a trend is stochastic versus a pattern? Or in other words, when a trend is actually just a random walk increasing over time versus when it is actually a trend? And the same question goes for seasonality. Okay,
it's a good question. And let me rephrase it a little bit, because when we refer to something a stochastic trend, what we're saying is that it's changing in time. So I think I referred to this in the presentation as a local trend. And here's the gist of that. There are times where data drifts. In other words, that the sales level may go up or down. And it's not really a trend. It's the fact that the sales levels are changing. There are other times where the sales levels are consistently changing in the same direction. And that's a trend. So and the way I like to think about this is, when I generate a forecast, do I want to forecast upward or downward movement, or do I just want to say the sales levels have been changing and I want to forecast the current sales level? Okay, how do we do this? 2-part answer. One is statistical methods like exponential smoothing and Box-Jenkins and other forms of extrapolation can use the properties of the historic demand history to automatically determine this. So the methods that can automatically either forecast a trend or forecast a level, assuming we have enough data, and for here I would say 2 or more years worth of data if you're doing it with months or weeks, they're pretty good. Okay, so if you have enough data, this can be done statistically. If not, then I guess the decision needs to be made using your own knowledge of the process. In other words, you'll know what the products you're working with are, and the question is, are we experiencing growth? Is this a demand for the product is growing, and therefore we will forecast it as such? Or is it just the kind of thing where, we have a number of customers, and maybe the number of customers changed, and therefore our levels change, but we don't really want to forecast continued growth because we don't anticipate new customers. So again, 2 ways of doing it, either quantitatively through the data, and that's often pretty straightforward, or using your own domain knowledge of the subject. Seasonal patterns were the second part of that, and those I think are even easier in some ways because, again, with knowledge of the data, most forecasters are going to have a strong, correct, preconceived notion of, do I have seasonal demand? To get at it statistically, again, that's a question of, do I have enough data? And for the seasonal patterns, you really want ideally more than 2 full observations of the seasonal cycle, which means more than 2 years worth of data. Once you've got 3 or 4, it's very easy to nail it down. If you have less than 2, it's very hard to nail it down, and you should really be relying on your knowledge of the data. But excellent question. What's our next question? Okay,
thanks, Eric. And one more question. Lots of great questions here, by the way, and so rest assured we'll get back to everyone via email after the webinar is over. So our last question for now. In terms of the component model, and I guess specifically what you showed in Forecast Pro, could we use that to forecast new products, and how could I build in some assumptions to use that technique for new products?
Okay. Quick answer, yes, you could. Okay. We actually anticipate that one of the main uses of this will be when I don't have a lot of history. Okay, so new products. And I think the key there is when we think of this component model, let me go ahead and put the graph back here, is what are the components? Starting point, trend, seasonal pattern, events. And the question is, can I estimate any of these from the data? You can start to get at a trend with as few as 5 data points, but until you have more data, getting at the seasonality is going to be tough. So, for instance, I have a new product. Let's say it's a product line extension, and I want to pull in the seasonal pattern from a different product. That's very easy to do. And I can actually, we have something called helpers where I could just grab the seasonal pattern from a different product and pull it right in. So I do think, again, because it's a new model and it's still in beta test here, we're still discovering all the uses for it, but it's pretty clear to me that new product forecasting is going to be one that people will use this for quite a bit. Okay, so again, I have a tendency to talk, I'm afraid. So I went a little past our time, but I want to thank everyone for taking their time out of your day to join us and learn a bit about components of data. As Eric mentioned, we had lots of other questions come in. We will be answering them via email, so rest assured you will get an answer. And hopefully we'll quote unquote, see you next time at our next webinar in April. So thanks again for attending.
Muted.